Okay, we've been talking about stoichiometry and how to work stoichiometry type problems. So remember, there's kind of two types of stoichiometry problems. There's sort of basic stoichiometry problems, and what makes them sort of basic is you're really only given one piece of information about somebody in the equation. It may be a reactant, maybe a product, but really kind of only one piece of information that you could really convert into moles. And for those sort of basic problems, really, there's four steps that we follow. Always, we want to balance the equation. We want to convert to moles. So whatever unit they sort of give it to you, and you want to definitely convert to moles. Usually that does involve the molar mass. To do that, at some point you get to grams, and then using the molar mass from the periodic table, go grams to moles. You then want to do the mole to mole relationship. And that really is what stoichiometry is about, is sort of the third step here. We use, as we talked about last time, really the equation as a conversion factor. Again, really in these type of problems, we're given information about something in the equation that we're really not interested in. So we need a way to kind of convert to other substances in the equation. And that's the mole to mole relationship. So again, instead of sort of looking it up in a table or anything like that, we get the actual conversion factors from the actual balanced equation. Lastly, we want to take those moles, which you should be in at that point, into some other unit. Again, molar mass here on the back end is a very common sort of ending to take the moles back to grams using the molar mass. So these are really the four basic steps for a basic stoichiometry problem. Like I said, you pretty much just have one piece of information given to you. We also talked about limiting reagents and excess reagents. And the idea of limiting reagents is there will always be sort of a reactant that gets used up first in the chemical reaction. And the sort of consequence of that is it is really the one that determines how much product you'd be able to make. So, as we talked about last time, if you're just kind of putting together A plus B to make A and B, and if A was your limiting reagent, at the point where A is no longer available, there's no possibility of making any more product at that point. So, because it is a limiting reagent sort of situation, we do need to sort of determine which one is the limiting reagent because we need to use that amount to figure out how much product that we would make. So it is really the defining sort of guy that determines the product that's going to be made. Obviously, your excess reagent is the guy that you have plenty of, and you actually have some of the excess reagent typically left over at the end of the reaction. Um, the difference between sort of a basic problem and this limiting reagent problem is in a limiting reagent sort of situation, you pretty much can calculate the moles of each reactant. And so basically, based on the information given to you, you are able to pretty much turn that information into moles of each reactant. And that is really the key of at some point, you do need to figure out which one is the limiting reagent. Now, as we talked about last time, there's many a few different ways that you could kind of do these type of problems. One way, as we talked about, is basically still using the four steps here. And right about here, you will do a calculation to determine the limiting reagent. And again, the idea of that calculation is you could choose either reactant. And basically, what you want to figure out is if you want to use up all the starting amount of the first reactant, how much of the other reactant would you need to completely react that with? So that's just a basic kind of mole to mole relationship between the two reactants. What you do when you get that number is you compare it to the amount of that reactant that you're starting with. And if you do have enough, then that's the excess reagent. If you do not have enough, then that is the limiting reagent. And at that point, you would continue on with the limiting reagent and do the other steps, the mole to mole relationship using their limiting reagent. and taken our moles to some other unit. We also talked about that, again, very commonly taught by people, is just say if you had, for example, the starting amounts of A and B, to do, for example, just two separate calculations, starting with A first and figure out how many grams of AB you would make, starting with B, do a separate calculation, figure out how many grams of AB you would make. And the one that basically produces the smaller amount of grams, for example, would be your limiting reagent and your theoretical yield. So that's, again, another very common way that people are taught to do limiting reagent type problems. Perhaps a new way for everybody, and again, the benefits of what we were talking about last time is, again, is something that you would use as you go to 200B, is you could take the ice table approach to it. And again, the idea of the ice table approach is, I'll just maybe put something like that here. You basically convert everything into moles. So really, regardless of any of the sort of steps that you choose or pathways that you choose to do these type problems, the first two steps are always the same: balance the equation, convert to moles. Initially, you would take the initial moles of A, you take the initial moles of B, and 0 for your products. Remember, the change part is really important because it does take into the mole-to-mole relationship. So you got to take the coefficients. We should expect our reactants to be decreasing with time. So 2x, again, the 2 for the coefficient, minus 2x, and plus 2x here. Again, it should be increasing, so that should be a plus. At the end here, we just bring it down. And again, to determine our limiting reagent, we set each of the reactants basically equal to 0, and you solve for x, and the smallest x is your limiting reagent in that case. And the nice thing about this, as we saw last time and talked about, you can then really very quickly probably solve for anything that you're asked for, how much of any product that you're making, how much of the excess reagent left over. Again, when you put that X into here, X would be the moles here as the units, and those can go again into here, basically. Any questions on any of those sort of steps there? All right, so let's talk a little about yields, which we sort of touched upon as we were doing some of those examples last time. There's a few different types of yields that we come across. The theoretical yield. The theoretical yield is the amount of product that you would make as a result of the limiting reagent. The theoretical yield is pretty much your maximum yield. It is based pretty much on the equation, the stoichiometry, and how much of a reactants you're starting with in terms of the limiting reagent. It is as everything went perfectly correct. Everything went nice. There was no side reactions. You weren't a klutz and spilled it on the floor or anything like that. Everything went perfectly based on the equation, based on how much you're starting with. That is actually how much you should produce, which is your theoretical yield. As we know, nothing in life is usually perfect, so reactions aren't perfect either. Sometimes there's side reactions, sometimes you lose things along the way. Not everything gets transferred across. And that brings us to the actual yield. And the actual yield is the amount of product that you actually did make when you did this reaction. In textbook problems, typically this is given to you in problems. Obviously, if you're doing a lab, that would be how much you actually got when you physically did the experiment. But the actual yield in textbook type problems are typically given to you. The theoretical yield is oftentimes something that you do need to solve for. It's basically stoichiometry problems that we've been talking about. It could be a basic stoichiometry problem. It could be a limiting reagent type stoichiometry problem, but you usually have to calculate the theoretical yield yourself. That brings us to the third type of yield, which is the percent yield. And the percent yield is the actual yield divided by the theoretical yield times 100%. And that will give you the percent yield of that particular reaction. Percent yield, unlike percent error, percent yield, we do want kind of a high number. That means, everything went pretty well. In the 90s is pretty good. Do we want over 100% yield? The answer is, well, you could get over 100% yield, but in most cases, there's usually some type of error that's probably happened. So usually you do not want over 100% yield, but it can definitely happen. Very common way that it sometimes happens is, as we'll see maybe a picture, but maybe you make a precipitate through a precipitation reaction and you filter it. And when you pour it through and you catch all your filter or your solid on the filter paper, you need to usually let it dry because it's obviously liquid that went through there. But sometimes people don't let it dry very much or completely dry, and you still have some water molecules on there. So when you go reweigh it, you now have a lot more mass than you should because of all the moisture and stuff without from the water. And you can end up with actually over like 100% yield. So that's a very common place in the lab that sometimes happens is people are impatient, don't let it completely dry out, and you get some excess sort of water weight. When you go weigh it, you have a much higher actual yield than you should, and you end up with over 100%. So in reality, it is possible to get over 100%, and in most cases, that is not a good thing. So usually close to 100% is good. Like I said, 95, 96, 97, those are all really good. If you got like 10% yield, you lost a lot of product along the way when you were doing this type of reaction. Any questions on that? Now, when you do this calculation in terms of units, a lot of times it is grams over grams, but it doesn't necessarily have to be, as long as they're both the same unit. So you could actually do moles over moles or, whatever sort of units you want, as long as the actual yield and the theoretical yield are technically in the same units, you could put it in there and do it. Most of the time, though, you usually are asked to solve for grams. So usually it's like grams divided by grams, but technically you could do it with moles over moles or as long as they are really the same units. All right, so let's take a look at one. Maybe let's try this one here. Maybe slightly different numbers. So we'll use these here. Why not? We'll give it a go. All right, so why don't you give it a go here? We have this equation. We want to calculate the theoretical yield of TI in grams, and we also want to calculate the percent yield if we produce 0.542 grams of TI when it's all said and done. And TI is 4788. I think the other molar masses are calculated for you, so that's pretty good. All right, so see what you come up with. So first off, we are given 2.46 grams of TiCl4, so that is a reactant. We're also given 1.13 grams of magnesium, that's a reactant. We're given the grams of each of them. Obviously, they also give us the molar mass, which you can go to periodic table and get if they didn't. But because of that, we definitely can get to the moles of each of these guys, and that is the key, that this, again, is going to be a limiting reagent type situation because, again, you can definitely get to the moles of each of those. So here we're looking for the theoretical yield, which, as I mentioned before, is something that you typically do need to calculate. Ultimately, as well, we're looking for the percent yield. And the percent yield, as we just saw, is the actual divided by the theoretical times 100%. In this case, we actually produced 0.542 grams of TI, and that is our actual. And as I mentioned before, typically in book problems, that is definitely given to you somewhere in there. So it is really the theoretical that we do need to calculate through stoichiometry here. And because it's a limiting reagent problem, we basically need to take that step to do that. Regardless, as we talked about, there were three different ways that we sort of touched upon. You could do these type of problems. Again, you could do either way that you choose that you're comfortable with. But really, either way, the first two steps are the same. You want a balanced equation, which in this case it already is. The second thing that you want to do is convert to moles. In this case, we do need to do that. So we'll start with that here. We'll take 2.46 grams of TiCl4. Again, they were nice enough to give us the molar mass, but if they didn't, you would go to the periodic table, add everybody up and get it. And that will give us our moles there of this guy, which is 2.46 divided by 189.7. Looks like 0.01297 moles of TiCl4. We'll do the same for our other reactant, 1.13 grams of magnesium. And again, they gave us the molar mass from the periodic table of 2431 grams per mole. And that's going to give us 1.13 divided by 24.31. Going to go 0.04648 moles of magnesium. Any questions up to there? Yeah. So now we get into really the theoretical yield and stoichiometry part of it. So maybe I'll borrow the equation here. So I got TiCl4 plus 2 magnesiums, Ti, and 2 MgCl2. All right, so once again, I'm going to use the ice table here. So I'm going to go with initially for our Ti Cl4, looks like it is 0.01297 moles. For our magnesium, it was 0.04648 moles. Again, we could go with 0 of each of these. Change, this is going to be minus x because the coefficient here is 1. Going to be minus 2x because the coefficient here is 2. That is going to be now on the product side. We're going to add these guys because we're gaining. So plus x, coefficient there was 1, and plus 2x at this point. We now can bring everything down here, 0.01297 minus x, 0.04648 minus 2x, x, and 2x. Any questions on the table here? So remember, at this point, this is where we can pretty quickly figure out our limiting reagent. We're going to set each of these equal to 0. And when we do, this first one is pretty simple. It's the same number, so that's going to be 297 moles. Here, we're basically just going to divide by 2, as that will give us basically 2x equals 0.04648. So basically just going to divide it by 2. And that will give us an x value of 0.02324 moles. Again, in this case, we are looking for the smallest. And it looks like it is this guy, so we do not need this number. That tells us at this point that this guy here is our limiting reagent, and this one right here is our excess reagent. Questions on that there? All right, so the nice thing about this is that x is pretty much all the x's that we see here in the end line. And since we're actually looking for Ti in this case, we could see just from the table that the moles of Ti equals x, which means we have basically 0.01297 moles of Ti. We now can use the molar mass, which was, I believe, 4788 grams per mole of Ti, and get that into grams. So we'll go 0.01297 times 47.88. Going to give us 0.621, and that is going to be grams of Ti. That also will be our theoretical yield. Any questions on that there? Again, as I mentioned, not asked in this problem, but the nice thing of using this sort of method, for example, if I also want to know how much magnesium chloride I produced, the moles of magnesium chloride from the end there is 2 times x, which would be 2 times 0.01297 moles. And that would get us 0.02594 moles of magnesium chloride. You then could use the molar mass of magnesium chloride, which is 2431, I believe, plus 2 times 3545, something like 95.21 grams per mole. And that would then get you something like we produced 2.47 grams of magnesium chloride. So pretty quickly we could get there. We also, as we've talked about, could put that X back into here to figure out how much of our excess reagents left over. And we would do that by just putting in our X value there. So 0.04648 minus 2 times our 0.0129 moles here of magnesium will get us 0.04648 minus 2 times 0.01297 gets us 0.02054 moles of magnesium. We could use the molar mass of magnesium, 2431 grams per mole. And again, as you can see, we would have something like 0.4993 grams of magnesium left over. In this case, I think we started with, what did we start with there? 1.13 grams of it. So you can see, again, just to illustrate very quickly, you could pretty much solve for anything that you might be interested in. We should also probably solve for the other part of this question, which was the percent yield. So let's do that. So our percent yield is our actual divided by our theoretical times 100%. And our actual in this case was 0.542. 0.542 grams divided by our theoretical. Again, we're going to use the theoretical, obviously, for TI, since that's what the actual is. So we don't want to use, obviously, the 2.47. 0.621 grams times 100% means in this case, we actually had a percent yield of about 87.29%, or 87.3% in this case. Not terrible type yield, high 80s, I guess. Any questions on any of those steps there? So again, this is one approach. If you like it, like I said, it's quite useful and can really allow you to solve for anything that you need very quickly. Also, again, the added benefit is that's pretty much the calculation 200B. If you're going to continue on, you pretty much will be doing those type of calculations. Any question on any parts of that one there? All right. Let's get this one. It's kind of similar here. Let's do. All right, let's do this one here. If we take 100 grams of ammonia and 100 grams of carbon dioxide, and we produce 120 grams of NH2CO, what is the percent yield here? So some numbers here: nitrogen 1401, hydrogen 1.008, oxygen 16, and carbon 12.01. All right, so see what you come up with. Okay, so let's take a look. Once again, here we are given 100 grams of NH3. We're going to react with 100 grams of CO2. So that is, again, information about both reactants. We definitely have grams of both of them. Again, that means we can get to moles of each of them. So once again, this tells you it is a limiting reagent type of problem. We do have that we produce this much here of our product, 120 grams, and that's going to help us with our percent yield, which again is our actual theoretical times 100%. So that is obviously going to be our actual yield here is 120 grams. So we do need to, again, use stoichiometry here to solve for our theoretical yield. Once again, first couple of steps the same. We got our equation balanced. We do want to convert into moles, so 100 grams of NH3 going to the periodic table. We got 1 nitrogen at 1401 and 3 hydrogens at 1.008. Going to yield us 1703 as our molar mass. That's going to give us 100 divided by 17.03. Going to go 5.872, we'll call it, moles of NH3. We also need to do the same thing for our CO2. So we got 100 grams of CO2 going to the periodic table, one carbon at 12.01 plus about 32 there for your oxygen. That's going to give us 4401 grams per mole for our CO2. And that will get us here 100 divided by 4401, about 2.272 moles of CO2. All right, so once again here, I'm going to use the ice table approach. And just so we're clear, I would say, again, the ice table approach is really good for limiting reagent type problems. If you have a basic stoichiometry problem, I would probably just do the 4 steps we talked about yesterday at the beginning without really the ice table. It's not really necessary because in a basic stoichiometry problem, you kind of already know the limiting reagent if that's the situation already. So again, I would probably reserve the ice table approach for really just limiting reagent type situations. So this is that situation, so we'll use it here. NH3, CO2, NH2, 2CO, and H2O. So again, initially we're going to put our moles of each of these guys. So we got 5.872. We have 2.272, and again, 0 and 0. Change, again, we want to make sure we take the coefficient into account. So minus 2x there, coefficient here is 1, minus 1, coefficient here is 1. This is going to be plus, though, on the other side, and this is also 1, which would be plus x. That means at the end here, we got 5.872 minus 2x, 2.272 minus x, x and x. Once again, here we can now kind of really quickly figure out our limiting reagent by just simply putting them equal to 0. And essentially the x value here is 2.272 moles. And we're basically just going to take 5.872 and divide it by 2. And that's 2.936 moles. Once again, we are looking for the smaller value of x, and that will be our limiting reagent. So in this case, it is the CO2 is our limiting reagent. That does mean the NH3 here would be our excess reagent. Any questions on the table there? All right, at this point, we are really interested in our product here, so we can get our theoretical yield, and we can see that from the end there that the moles of our product here are NH2, there was parentheses, 2CO will equal X. That means that we do have 2.272 moles of our product. We do want grams because our actual yield was in grams, so we do want to convert it to the same units. So to get the molar mass here of our product, that's 2 times 1401 for the nitrogens, plus 4 times 1.008 for the hydrogens, plus a 1201 for the carbon, and a 16 there for the oxygen. That's going to be a 60.06 grams per mole from the periodic table for our molar mass of our product here. And that is going to get us then 2.272, about 136.5 of our product here. That would be our theoretical yield, which is what we need for our percent yield. So now we have everything that we need. So I will erase all this. We don't really need this now. We can now calculate our percent yield for this particular reaction here. And again, that's going to be our actual that was given to us, which was 120 grams, divided by our theoretical that we just calculated, 136.5 grams times 100%. And that is going to get us there about 87.91% in this case as our percent yield. Any question on any of those steps here? Again, we don't need to do it in this problem, but if we wanted to get the water, we could also have basically 2.272 moles of water, which we could 10 times by 1802 to get the grams. We also could go back into here and figure out how much of our excess reagent is left over. Any questions on any part of that there? Okay. All right. Question on limiting reagents or stoichiometry in general. Again, as I mentioned before, ice table probably best used for a limiting reagent situation. Kind of just a basic stoichiometry, setting it up for steps 1 through 4 for a non-limiting reagent type situation. Um, any questions? Yeah. So when you start to use it for stoichiometry, like let's say it's a limited equation, then would we use the divided number or would we use the So you always want to, if you're doing the let's get back there. So if you're doing the ice table approach, you want to use the value that you get at the end here. That's the smallest to go back into each of these. So that is what, again, that value is for and stuff like that. You do not want to use the beginning number or anything like that if that's what you're asking. Now, if you do it sort of the non-ice table approach where we kind of did the calculation where we figure out how much of one reactant that we will need to use up all the other one, at that point you do need to go back to and use the original sort of moles and stuff like that. But here, this sort of takes it to the end and gives you basically the change part, which is what that X is. So definitely on the ice table approach, it's always that last number when you solve for X. That's the smallest, and that's the X value that you should go into here, because this is basically at the end of the reaction. That's what the E sort of stands for here, is the end of the reaction. That's ultimately what you're trying to figure out, is like what's there at the end. And the X is actually the change part that happens. It's how much is actually lost as this reaction is going on and stuff like that. So that's definitely the number that you want to use. What's that? If you do not do the ice table approach, so for example, if we did, oh, let's just say, so let's just say we had this equation, something like this. Let's do this here. A, E, 2B, let's do something like that. And let's just say initially, we're not going to do an ice table, but let's just say we had 4 moles of A to start with and say 2 moles of B to start with, and we're going to mix these guys together. So the other approach that we talked about, which is sort of the non-ice table approach, is we could figure out how much B we would need to use up all of our A. So this is like our starting amount. So if you did 4 moles of A and do the stoichiometry there, we have 2 moles of A and actually I'm gonna make this 3 just to make it easier. We have 1 mole of B in this case. And in this case, if we do that, we would need 2 moles of B here. And that is how much is needed. And when we compare, we could see that we do have enough of B in this case. So that would mean that this is the excess reagent and this is the limiting reagent in this particular case. And what I mean by that, in this case, you wouldn't use this or any of these numbers. You want to go back to the starting amount and then just do a basic stoichiometry problem of 4 moles of A, 2 moles of A to 1 mole of A to B, and continue on that way when you do it. So if you take this approach where you do this little calculation here to figure out how much of one reagent you need to use up the other, then you want to make sure that pretty much you wouldn't use this calculation or the result of this calculation for much. You would always want to go back to the starting amount and stuff like that. Other questions? All right. So then let's talk about a couple other things here. We're going to talk a little bit about solutions and concentrations and solution stoichiometry. So before we talk about solution stoichiometry, let's talk a little bit about solutions. And a solution is a homogeneous mixture of two or more substances that are together. And really, a solution is made up of two things. There's the solute, which is the smaller part of the solution, and the solvent, which is the larger part of the solution. So that is the smaller part, and that is the larger part. Usually in a solution, the solute's dissolved in the solvent and makes a solution. And typically speaking, solutions are the ones that get the aqueous symbol next to them. So they are the guys that have that little AQ symbol next to them. Um, as we talked about, there is a difference between L and AQ. For example, to make a solution, you would take something like water, which is a pure liquid by itself, and mix it with something like sodium chloride. And the salt in this case will dissolve and make a sodium chloride solution. Here, the solute would be the sodium chloride, and the solvent would be the water in this particular case. Them together will make a solution of sodium chloride. The easy way to determine what is the solute when you have a solution given to you is the name of the solution is the solute. So if you have a sodium chloride solution, sodium chloride is a solute. If you have a magnesium chloride solution, magnesium chloride is a solute. So whatever the name of the solution is pretty much what was dissolved in it. A lot of times water, the solvent is water. It is not always the solvent, but water works really well for things that are ionic and things that are polar. So water is a good solvent for things that are ionic and things that are polar. Water, by the way, is a terrible solvent for something that is non-polar. So we will see this in a later chapter as well, but the idea known as like dissolves like. And the idea there is that things that are similar will be soluble in each other, and things that are not really similar will not be soluble in each other. And that means that things that are ionic and polar are usually pretty soluble in each other. Things that are polar and polar are soluble in each other, and things that are nonpolar and nonpolar are soluble in each other. So these guys are typically soluble and will kind of mix to make a solution. Things that are typically insoluble, which really will not mix, is something where you kind of cross over polar and non-polar. Those guys typically will not mix. So a lot of times water is a very common solvent for ionic compounds because water is polar. So because it's polar, it has a positive side and negative side. It works really well with ions that are charged as well. Solutions like soft drinks, water, sugar, CO2 is the solute. Air, nitrogen is actually the largest part of air, and oxygen, argon, methane are the smaller components. Solder, lead, and tin is sometimes used in that as well. So when we talk about solutions, like I said, one of the most common unit of concentration of a solution is molarity. And molarity is the moles of solute over liters of solution. Molarity is abbreviated with a capital M, and a lot of times people just say moles per liter. You could think of molarity as like a formula, just like density. Liters is equal to moles divided by molarity, and moles is equal to liters times molarity. So these are three very common sort of ways that we rearrange molarity, and I would say this is used a lot and also liters, but definitely in stoichiometry, that part of it is used a lot. When you have something in molarity, like you have 4.50 molar sodium chloride solution, it is really a very good idea, especially if you're going to do some type of calculation, to get rid of the big M and actually use both units. And what that means is there are 4.50 moles per liter of sodium chloride. The number stays with the moles part, and it's always per 1 liter. You could actually use molarity like a conversion factor and do dimensional analysis. You could flip it around and use it as like a dimensional analysis conversion factor if you needed to. Now, the reason I say you should probably use it in a calculation like this is most people, I would say, is when they leave the big M in there, they have no idea about the liters part. Not sure where it's at, not sure it's even there. They forget all about it. They just see the big M and think moles, and that's all they think. So I would highly recommend that you should always get rid of the big M when you're using it in a calculation. That way you can clearly see where the two units are. And I would also recommend probably that you do more of a dimensional analysis approach and set it up with the units and stuff like that. The reason it's really important is because when you use molarity, you need to, for example, in this calculation, you need to make sure that you have liters times the molarity so that they properly cancel it out. Now, if you take milliliters times molarity, they do not cancel out, but you can do that, except that molarity in this case is not moles per liter, it is millimoles per milliliter. And when you multiply molarity times that, the milliliters cancel and you end up with millimoles, which is not moles like you end up with here. And I would say most of the time you need moles, not millimoles. So if you're not aware of that, you will be off by a factor of 1,000. So you absolutely can multiply milliliters times molarity, but the difference is you get millimoles as opposed to liters times molarity, where you get moles. So it's really important, I would say, convert it to liters. If you are using molarity by itself and using it with the volume, definitely make sure the volume is in liters. There is a place we'll talk about in a second about doing dilution type problems where you can't leave it in milliliters because everything works out okay in that situation, but definitely keep that in mind because molarity most of the time is this, but molarity also can be millimoles over milliliters. The millis cancel out and you end up with moles per liter, which is the same sort of thing. All right. So calculate the molarity of a solution prepared by dissolving 15.6 grams of KBr in enough water to make 1.25 liters of solution. Potassium is 3910. Bromine is 7990. So take a moment there, calculate the molarity that you get. Yeah, to here. Yeah. Yeah. Okay, so let's take a look. We're calculating the molarity here of the solution. So once again, molarity is moles per liter. Prepared by dissolving 15.6 grams of KBr in enough water to make 1.25 liters of solution. So we actually do have already the bottom part here, what we need for molarity. So we are missing moles, but we do have grams, and obviously very common conversion in this situation is grams to moles, which as we hopefully know at this point should be our molar mass from the periodic table. So to do that, we will need really just to add these two together. That's KBr. That's 119 grams per mole when we add those guys together. And we will use that to convert our grams into moles. Again, using as like dimensional analysis here is 119 grams per mole. And that will get us here 15.6 divided by 119. Looks like 0.131 moles. That is the top part that we need. So now we can calculate our molarity is going to be 0.131 moles divided by our liters. And that's going to get us there 0.105. Now, in terms of the units, you can't leave it as moles per liter of KBr. R at this point, if you want to put the big M back in there, you can, of KBr. So you could go either way on that in this particular case. So definitely grams to moles is a very common sort of conversion. Also, a lot of times volume is given in milliliters. So milliliters to liters is a very common conversion as well. Again, 1,000 milliliters is 1 liter, something that you use a lot, especially in solution stoichiometry, going from milliliters to liters or liters back to milliliters. It's a very common conversion as well. Any questions on that one there? All right, so I want to try this one here. What is the mass of Ki that's required to make 500 milliliters of a 2.8 molar solution of potassium iodide? 3910 once again for our potassium, and iodide there is 126.9. All right, so let's take a look at this one here. We are using molarity, obviously, or we have molarity involved, which is again our moles per liter. In this case, we actually do have the molarity, and we don't have the liters, but we can convert to liters, so we do have that guy. So if you're not sure, obviously moles is what's missing, and moles is good because from moles we could go to grams using the molar mass. So if we rearrange this, the moles will equal our liters times our molarity. So in this case here, we do want to probably convert our milliliters into liters, which is a very common conversion. Again, like 1,000 milliliters is a liter. 0.55 liters in this particular case. Now, our molarity, as I mentioned before, when you're using it in a calculation, personally, get rid of the big M and use both units and just do it as a conversion dimensional analysis type situation where you could use it like this, or you could use it like this. And again, you could clearly see both units and how you should use it. And by doing that, once again, as we talked about, you don't even have to remember how to rearrange this. You could just think about it dimensional analysis wise of I need to get rid of liters. So liters are up on top. I need liters in the opposite direction or location, and I could just use that. This is Ki per liter. That way the liters properly cancel out here. We end up with 0.5 times 2.8. We'll go 1.40 moles of Ki. We do want the mass, which is typically grams. So once again, in this case, actually, we're just going to add these together. And that's going to give us 3910 plus 126.9, about 166 grams per mole. So we'll use that also as a conversion factor. We want grams up on top, so we end up with it per mole. Those will cancel, and we will end up with here about 232 grams of Ki. So if you were to make the solution, you would take 232 grams of Ki and measure it out. You would then dissolve it in enough water to end up with a total volume of 500 milliliters. And if you mix it up really good, you should have a solution that has a 2.8 molar concentration. Any questions on any of that part of the calculation there? So molarity again is a very common unit of concentration, and we will use it here shortly within stoichiometry as well. Now, another sort of aspect of molarity is, and sometimes in problems, we are maybe not interested in, say, the entire ionic compound. So, for example, when you take something, say, like calcium chloride, and you do have a calcium chloride solution, what happens and what allows it, for example, the calcium chloride to dissolve in something like water, which is your solvent, is the idea, as I mentioned before, that water is polar. with the oxygen part being more negative, the hydrogen part being more positive. So when you take something like calcium chloride and you dissolve it in water and it looks like it all disappears, what is actually happening within here is your calcium ions get surrounded by water's negative side, which is the oxygen side. And the chloride ions that are floating around get surrounded by the positive side of water, which is the hydrogen side. And that's what keeps those ions away from each other and why it also looks like it just disappears and goes away. And that's because it's surrounded by a ton of water so you visually can no longer see it floating around in there because it's just surrounded by so many waters that it's no longer there. We do know it's there, as we talked about maybe a couple of times, like in those experiments, when you evaporate off the water goes away, those guys come back together, and obviously they're able to, come back and reform the solid. But sometimes when you're doing problems, you may not be interested in like the whole ionic compound as a whole. You may be interested in, maybe the concentration of the ions that are floating around in the solution. Maybe you're interested in just the concentration of the calcium ions that are floating around, the chloride ions that are floating around in that particular solution. So if you had something like, say, a 2.5 molar solution of calcium chloride, and you were interested in what is the concentration of each of the ions that are present, it is based on how this calcium chloride would break apart, say, in water. And when it did, you would form a calcium ion and a couple of chloride ions in this particular case. And if the concentration of 2.5 molar for the entire solution there, ionic compound, is 2.5 molar, you could do kind of like a mole to mole relationship to figure out the concentration of just, say, the calcium. And if we look at the calcium ion from the whole thing, it is a 1-to-1 relationship, which means it is 1 times 2.5 molar. And the concentration of the calcium ions that would be floating around in that solution is 2.5 molar. Now, if you look at the chloride ions, it is a 1-to-2 relationship in this case. And how that affects concentration is 2 times 2.5 molar would get you 5 molar. So the concentration of chloride ions that are floating around in that solution is actually 5 molar versus 2.5 molar for calcium ions that are floating around. Concentration is not additive, so 2.5 and 5 doesn't add up to 2.5, obviously. It is proportion-wise. So if you just think about it, you get a 2-for-1 deal on the chloride, right? For every one of those ionic compounds that break apart in solution, you get twice as much chloride floating around as you do calcium. So chloride's concentration is twice the concentration of calcium that's in that solution. So that's the easy way that you can look at it if you had something like sodium chloride in this case, and was 2.5 molar. When that would break apart into a sodium ion and a chloride ion. In this case, it is basically 2.5 molar for this guy and also 2.5 molar for the chloride ions that's floating around. As it's a 1-to-1 relationship, you basically just multiply it by 1 in a sense. So that is the quick way that of how you could relate concentration of the entire ionic compound to the concentration of, for example, the individual ions that are present. The longer version of that calculation looks like this, so you can see it, but probably the shorter version is a quicker way to do it. So, for example, if we were looking at that calcium chloride, we would start with 2.50 moles of calcium chloride per liter. We would actually do a mole to mole relationship. So from the way it breaks apart, 1 mole of the whole thing gives us 1 mole of calcium ions. Moles of the whole thing cancel, gives us 2.5 moles of calcium per liter, which is our 2.5 molar of calcium ions. You do the same thing for the chloride, 2.5 moles of the entire thing over a liter. It is, as we saw, a 1 to 2 relationship there. So for every 1 mole of the whole thing, you get 2 moles of chloride ions. That will give us our 5 moles of chloride per liter, are our 5 molar of chloride. So that is where the 1 and the 2 comes from in terms of multiplying it by 1 or 2. You're basically doing the mole to mole relationship, and that is just the quicker way of obviously doing it. So if it breaks apart into a 1 to 3 relationship, you multiply the concentration by 3 and so forth. Any questions on that? And again, sometimes you are interested or ask questions about, again, not the entire ionic compound, but just this particular ion. Any questions on that there? All right, so once you try it here, for each of these, what is the concentrations of each of the ions that are present in each of these two? Okay, so let's take a look at it here. We'll start with A. Really, we just want to think about how this guy will break apart in solution. By the way, we do know it is going to be a solution because of the sodium being present. In terms of solubility rules, it is soluble in everything. So we have 2 sodium ions floating around, and we have a sulfate ion floating around. That means that if the concentration of this entire thing is 1.2 molar, if we were just interested in the sodium, it is a 1 to 2 relationship. So we would multiply the concentration by 2 here, and that would give us 2.4 molar for the concentration of the sodium ions. We would do a similar thing here for the sulfate, but it is actually a 1 to 1 relationship, which means we would take 1 times 1.2 molar will give us 1.2 molar for our sulfate ion. Any question on either of those two? For B, again, we'll start with really how it breaks apart. So K2CrO4. Also going to be soluble because of the potassium being present, soluble in everything, will also give us 2 potassiums in this case, and 1 chromate here. Again, if this whole thing is 0.75 molar, it is a 1 to 2 relationship. So that's going to give us 2 times 0.75 molar, and that'll give us a 1.5 molar for the concentration of just the potassium ions floating around. And again, it is a 1 to 1 relationship between that and the chromate. So 1 times 0.75 molar will give us 0.75 molar for our chromate. Again, in the second situation here, we have twice as much potassium as we do chromate for every one that breaks apart. So the concentration of potassium in that solution is twice as concentrated as the chromate ions that are floating around. Any question on either of those there? All right, we'll lay it up there for now.